All right, thank you for having me out here, and thanks for the coffee. I needed that right now. It's good. I'm going to start with something I don't usually, and that's why you shouldn't believe what I'm going to tell you. Okay, right? And I want to get that out of the way because I think you'll enjoy the presentation more. One is everything you're going to see here is simulation, and simulations are based on assumptions, and I'm going to point out the assumptions along the way. So if there's some assumption in here that you think is wrong or something, right? Our goal is to explore this. But then number two is the most important one, which is we don't yet have experimental evidence of this. I say yet because it's not like we're not trying aggressively. This is just a very new concept that we're working on. All that out of the way, I would invite you to think about, what I would like you to do is, of course, get some experimental evidence for this. And so I think of this as this kind of presentation as an open discussion to how we can do these types of things and what we could use them for, and all the different spaces they could be utilized. So the focus area is dynamic catalyst resonance, and that's a concept we've been, like I said, only been working on for about a year. And then, of course, my interest is mobile renewable energy, but I'm going to show you that there are other places we could use this. So if I think of renewable energy, I think of all the problems that are associated with it, but all the things, of course, it can solve. If you're familiar with the state of Minnesota, in green and red here is the population distribution. This is the Twin Cities. It's over half the population. And then everything up here is forestry. This is where Bob Dylan and Judy Garland are from. That's the Iron Range. It's where over half the world's iron came from during World War II. And everything about here and down is corn and soybeans. Okay, so almost everybody lives here, more than a half. And we have an enormous renewable energy potential, both in the forestry, but also in wind. There's this huge wind corridor in central United States, and there's more than enough wind energy here to supply more than Minnesota's needs. In fact, we could export it if we could. The question is how to do that, because we have all this power down here and all the people that live over there. And you could stretch a wire there, but it's not the most efficient way to do that. Of course, this problem is bigger than Minnesota. You can think about where most of the people in the world live, which is Southeast Asia, right over in here. And of course, the question there is, how do you utilize renewable energy in places like that with that kind of energy density? And places like Japan, of course, are very interested in this, and they have all sorts of ideas. One of which is, let's go to Asia or Australia and put up massive solar panel arrays. Let's convert that to ammonia. Let's put it on a ship and let's bring it to Japan. Of course, then the issue is, can we do this economically? Can we produce ammonia and hydrogen efficiently from solar panels? Can we put that on a ship and can we transport it? Now, the question around ammonia synthesis is a very well-known old problem if you haven't seen it before. We can take N2 from air. We can make hydrogen, which we currently make from natural gas, but of course, we're working aggressively on to make it from water, from electrolysis, from wind and solar energy, maybe nuclear. And we can hydrogenate the N2 and make NH3. And the problem is, if we look at the conversion, this is thermodynamically favorable at low temperatures, but the temperatures you need to activate this N2 bond are up here in the 400 to 500 range. So the commercial plants based on the Haber-Bosch chemistry process are up here in the 400 to 500 degree C range, where the conversion at equilibrium is only 15 to 20%. So if we had a more active catalyst, we could slide up this scale and we could operate in the 100 to 200 degree C range and get 80 to 90% one single pass conversion. Now that's of course a dream that we would like to achieve, because then we could scale down these kind of reactors. We could operate them at lower pressure, lower temperature. And that's of course been what we've been trying to achieve for the past half century. And there's a problem with this. Why was Fritz Haber so successful, and why have we have a really hard time beating him? And beyond that, there are problems all across catalysis. And the issue is quite simple. We think of a really generalized surface chemistry in the following ways. We can adsorb a species A to make A star. This can react on a surface to make B star, and then this will desorb. And in any sequence of events like this, we can think of one of those steps as being the slowest. One of these, and inevitably it'll not just be a little slower, it'll be a lot slower. So it might just be that the reaction here is really slow, like breaking apart N2 on a surface might be a problem. And so what we can think about is the relative energy of A and B, and as we bind B stronger by the Bell-Evans-Polanyi relationship, this activation energy is going to go down. So if we think about that, as we bind stronger and stronger, the rate of reaction goes up. But eventually this binds too strong, and I can't get it off the surface, and we switch from a rate limitation here at the surface to a rate limitation in desorption, And that's that maximum you see right there. And so what we're really doing is we have this Goldilocks approach. It's not too hot, not too cold kind of a approach here. We're balancing out the rate limitations and trying to find what matches the two between them equally. And so let me just say that there's a premise here in how we think about catalysis, right? And I would call it the premise of modern catalysis is a search for advanced materials. Right now we think of a reaction as starting here and ending up over there, and some sort of unapproachable gas phase process where the transition state energy is just way too big. And so we think of a catalyst that we could absorb something to, could have a smaller transition state, but then we also have to account for the desorption energy. So a magic material does something kind of in between, right? It absorbs weakly, but has a much smaller transition state, right? And if we think about, if we can look for something like a zeolite or a MOF or a nanoparticle or a single atom, we can find some combination of absorption and geometry that's able to do that. And for a lot of systems, we've looked for decades, and we have not been able to find these kind of magic materials that take us beyond where we're stuck. And this is across all sorts of chemistry: methanol synthesis, ethylene epoxidation, all the chemistries we've pushed and we've pushed and we've searched. And we make incremental improvements in a lot of these chemistries now. Industry has said this is probably the best we're going to do. And so we need a whole different approach than just nanostructured materials. And so one idea that we've been thinking about is, well, what if instead of a static system, this Goldilocks approach of picking one system that's good for everything, what if the system changed with time so that we could take each part of the sequence and match the performance needed for that to speed up the whole process? And that's the idea of an energy diagram or a material in concert that's changing with time. So I could have A here, it could absorb as A star. It could then react all the way over to B here, and then once this is formed, we could flip states or switch it to another state to make B star, which could readily desorb. And we impose work to lift this from this state to that state right there. Now, when we do that, what we're essentially doing is we're picking two states on the diagram, and we could pick any two states we want. I'll show you, we can actually screen all the different conditions. But we could think of some descriptor. In this case, I'm using this binding energy of B star here as one state here and one state there. And of course, I can have any waveform here. I could switch instantaneously, like a square wave, or I could have a sinusoidal wave, and I can go between the two. The question is, where will I end up? Because I think of this line here, the Sabatier curve, as the steady state solution of the balance of all the steps. But when I'm doing this transiently, I could end up anywhere I want. Anybody who's operated a chemical reactor knows when you first turn it on, you get immediately, instantaneously fast rates until the system slows down to the steady state. So what we would like to do is constantly flip it, so we're always in that transient condition. If we flip it too slow, we'll end up here, and we'll end up right there, which will be slower on average than the static optimum. But if we keep increasing the speed at which we're applying the dynamics, we'll eventually reach a point where we can match the natural frequencies of the chemistry here and here. And that's what we'd like to do. So that was an idea I've had for almost a decade. And I'm an experimentalist by nature. It's very weird for me to give talks with simulations and lots of math. So my idea has been for 10 years, how are we going to try this? And eventually I gave up and said, well, let's do some simulation to understand it. And so we're going to take the very simplest case possible. We'll just take a perfectly mixed reactor for simplicity. We'll start with just a very simple reaction, A to B. We'll let every step be reversible. We'll have the kinetics of every step. We won't assume anything is equilibrated. And we'll have all the normal parameters we have: space velocity, temperature, and pressure. We'll have all the normal catalytic chemistry parameters we have. But now, because we impose dynamics, we have double the number of parameters of a normal system. We have the amplitude of the oscillation. We have the amplitude position, which we could slide left and right. We have the frequency, and we have the waveform type: square waves, triangular waves, all those kind of things that we could impose. And so what do the results of a simulation look like I could take something here, this reaction of A to B, and flip the relative binding energy of B back and forth. And again, this is relative, so don't worry about is it positive or negative, what does that mean? Just know that I'm binding stronger, then I'm binding weaker, and then I'm binding stronger, then I'm binding weaker. And every time I flip this state, you can see here that the surface coverage is changing between being covered in A to being covered in B, A, and B. And every time I flip, I'm pushing off a certain amount of material. The instantaneous turnover frequency goes up and then drops as the surface is depleted. And then I flip a second time, and I give off more A, and it's depleted. And this continues on and on and on, and eventually comes to a steady state transient system. So eventually, when I average this, the average turnover frequency will become rigid. Now the question becomes, what happens when I change the frequency? So here's a system with where I impose a square wave. This is the instantaneous turnover frequency. It starts out here on a static system where I'm not changing anything at the Sabatier maximum. So this is the best I could ever do with a static system. And if I impose a really slow frequency, here's 1,000 seconds time scale between changing, it does exactly what you think. It behaves like two static systems, a really slow reactor, then I change it to another state. It has a little bump here, which is not an artifact. I looked of the simulation. That's that benefit you get from flipping. But then it immediately comes to steady state, and it's just not a great answer, right? If I increase the frequency of this, eventually at 0.25 hertz, I'll match my average turnover frequency to the steady state system. And above 0.25 hertz now, I'm actually beating the conventional Sabatier system. And this is X scaled to match whatever particular system I have. You can see here the time scale is 0.1 seconds. And up here at 1,000 hertz, what's happening is I'm flipping so fast that I'm not completely changing the surface coverage between all of A and all of B. That's why I've attenuated the signal here. If you zoom in, you can still see it's actually oscillating back and forth. And here you can actually see, even though it's oscillating around this, it's slowly approaching its long-term steady state transient behavior. So what does this look like when I put everything together? So here's a system where I've averaged out the turnover frequency with time. And here you can see these are the square wave frequencies I've imposed on my catalyst surface. And you can see here's the static optimum right there, and it's right around this sub-hertz, 1 hertz range where I start to match that. But down here at low conditions, low frequencies, I'm not doing very well. And eventually I go up, and eventually I've matched the frequency of the chemistry, and I can't accelerate it any faster. But at that point, on this case, I'm 2 orders of magnitude above what I can get by a conventional system. And eventually what happens is I'm flipping so fast, I can't fill and unfill the surface anymore. And I've exceeded my ability to actually fill the surface, and the rate just plummets back down to a system that behaves more like a static system. So that's one particular amplitude. That's, I believe, 0.6 electron volts in flipping between 2 different energies. So a 0.6 electron volt energy is right here. So you could see it was actually slow, and then it shot up, and then it plateaued, and then it came back down on the other side. But one thing you can think about is not only if I keep the frequency fixed right here, let's say I'm at 10 to the 3, as I increase the amplitude of the oscillation, I actually get further and further out on my volcano plot, which I'll show you in a minute, but my rate actually goes up tremendously. So over here now I'm on the order of 10 to the 3, or 1,000 turnovers per second, which, you know, you're at the limit of what you could actually do in a real system because of diffusion limitations or something like that. But now we're talking about range of things like enzyme turnover frequencies, which would be astounding to achieve with a metal. So that gets to, that's one particular kind of case. But if I think about all chemistries have different scaling relationships. And this is one of the key concepts in catalysis, which is, if I think of the relationship between one species on the surface and the other, there's a linear relationship between the total energy in between, this is the BEP relationship, and the transition state energy. And so if I look at different dynamic systems, I have to think about all the different possible chemistries. And one possibility is that this relationship here, this alpha and beta, and the linear relationship between activation energy and surface reaction energy can change. And you can think of this back to the picture of the volcano plot at something that has a large alpha. This is an alpha of 1. That's pretty steep. I get a nice sharp volcano, and a small amplitude will give you the highest possible turnover frequency. Whereas if I think of something kind of mid-range, and here you can see the volcano starts to tip over. Most things seem to fall in this range right in here. If you imagine something like this, this is an alpha of 0. No matter what I do to the surface enthalpy, I can never possibly change this activation energy, right? Because it's always flat. I can never exceed that rate, because there's no way to manipulate the activation energy of that particular reaction. So luckily, I don't know of many systems like that. So what I just said in words, you can see visually here. Here's that really steep curve. And if I think about different activation energies, here's 0.6, 1, and 1.5 EV. These are enormous shifts in binding energy. But you can see that, you know, if it was possible to do a 1.5 EV shift in binding energy, which I think that's pretty far out, you would be up here on the insanely high turnover frequencies that would never even be achievable due to diffusion limitations. And you can see that right here as a bar plot, right? If I go now from an alpha of 1, now this is down to an alpha of 0.4, you can see that this broadens, and my return on amplitude goes down to the point where if I go one more further, I'm going to go from an alpha of 0.4, you can see now that this is completely flat. And no matter what I do, I can't exceed this turnover frequency limited by the reaction. So you need some ability to manipulate the reaction chemistry and manipulate the desorption energy, which makes conceptual sense. You need some ability to make every single step faster or slower. Now, of course, shape matters. Like, we're going to talk about how you would implement this experimentally. That's what we're working on. But you could imagine I could use a square wave with something electrocatalytic. It's possible to get very fast transitions, in fact, in excess of kilohertz. Other systems that are more mechanical in nature might not be able to get that kind of response. So a system here that has a sinusoidal response will again do the same thing. I might have a 0.6 EV in binding energy shift between strong and weak binding. I'll have a surface coverage that oscillates between low coverage and high. And actually, this system is fast enough that I don't go all the way down to complete either species. And then again, I get these turnover frequency responses here that correlate with the flips. But what you see is if I think about all the possible waveforms, these are 4 different possible waveforms we could consider. These are 4 different frequencies all applied to the same chemistry with the same amplitude, is that the square wave outperforms all the other waves. So the more time I spend at the extremes, the better. And what I think of that is, I'm trying to match the conditions of each possible catalytic state to that particular rate limitation. And when I spend time in between, like in a sinusoidal wave here, that time is not optimized for any particular step. And so I can think of sort of efficiency in here, how good our system does at optimizing for each particular series of reactions. Now, that's for chemistry variations and for waveform variations. There are other variations here that become important when you think about a dynamic system. This is my starting gas phase species energy. This is my product gas phase species energy. Right, they're offset by the heat of reaction. I was talking before about how the transition state energy changes. This is that activation energy, which is a function of these 2 linear scaling parameters, the BEP relationship parameters. That's well known. But the other thing that shows up now is interesting, is how the intermediate energies change. So if I think about it, I was talking about moving around this energy of B star right here. It could be in state 1, 2, or 3. And so whatever I'm doing, I'm imposing an electric field or I'm imposing a strain on the surface. However I'm manipulating this right here, might be photocatalysis, it's going to interact with different species differently. So this one might change a lot, but this one might change very little. And so the relationship between the enthalpies of the surface species can also exhibit a linear scaling relationship, which we can say is a function of 2 parameters, just like a conventional BEP relationship. And I can show you that on the next slide as another way to think about this. If I think of the heat of adsorption of 2 different species, right, in a A to B reaction, here's the heat of adsorption of B, and here's the heat of adsorption of A, there's some point, I'm going to split back here, where these 2 have the exact same energy, okay? In this system right here, that's this delta point right there, where they're at the same energy. And that's important, and I'll explain why in a bit. So that's a common point between the 2. And then I also have the slope here, which is the relationship between how the 2 change. And that's, of course, intermediate dependent. So different chemicals respond differently. Different catalysts behave differently, different surfaces. But also, I can think of different perturbation methods, however I'm using to manipulate the binding energies. So let me give you some real systems here. This is not me manipulating a single surface. This is just showing that this is linear across different materials. Here is 2 surface species that are important in the ammonia synthesis reaction. Here's NH star and NH2 star. Here's the heat of adsorption of NH star and the heat of absorption of NH2 star. On rhenium, ruthenium, platinum, palladium, and gold, these are all from the Mavrococcus group at Wisconsin. And you can see that they differ by this ratio of 0.5. So depending on how you define your gamma, it's either a half or 2. Depends on which way you're going in the reaction. These things have to do, in this case, with how they're coordinated, right? This system here, where NH star has fewer protons on it, will interact with the metal differently. And you can even see then that the ratio, that slope is 0.21. It's reduced significantly. Now, another way to do this is with electric fields. And Josephine McEwen's work at PNNL and Washington State has looked at this, probably, I think, more than anybody, where he looks at molecules on surfaces And then he imposes an electric field to this. He can actually manipulate the binding energy. So here is the applied electric field in volts per angstrom, which is enormous. That's an enormous electric field. And so you couldn't put a reactor in between two plates and do this. It would arc before that. The only way this could be done is something like an electrocatalytic system, where you have a metal double layer that's very, very small and gives you very concentrated electric fields, but it is possible to do. You can see here I'm getting a shift of about 0.6 electron volts, which is exactly the range I was showing you earlier for this particular formaldehyde on, I don't know if I said which one, oh, on nickel in this case. So it is possible to do this electrocatalytically. Other examples here would be something like surface strain. This is one that's been studied extensively, where as I strain the metal, I'm actually changing the electronic properties of the metal. That changes the interaction of the adsorbate with the metal electronic structure, and I can actually shift the binding energy. This one is well studied. Unfortunately, it's not very powerful. And I can show you that in this slide right here. So what you're seeing here is each of those two methods side by side. And what you see is, this is the adsorption energy of methanol versus three different things. Here's hydrogen, formaldehyde, and methane. And what you see here is that methane, first of all, adsorbs weakly, as you'd expect, but it also has a very small slope. So while my methanol energy can move a lot, my methane energy moves very little, which makes sense. Hydrogen moves more, but still not very much. It still has quite a low slope. And there's even bizarre things that can happen. I can take methanol and move it quite a bit. And as I make this stronger, I can actually make something like formaldehyde weaker, which means it would have a negative slope. That's a really strange case, but these things exist. Now, if you look at the second set of data here, this is the Mavrocorkis group work on strain, where they've looked at the adsorption of oxygen and carbon monoxide binding energy. And what you see is, even over the case of significant strain, I think this is 3% strain, which is not even physically realizable except in a simulation, you're not getting the binding energy shifts that are actually possible. But you still see, again, based on his simulations, that it's linear in the behavior between these two. Now, how could we implement this electronically? I was saying earlier that electrocatalytic approaches might be the best. We've come up with 7 ways we think this is potentially possible, and this is one for sure. If I have a metal surface here, and I impose a charge, I have to balance that charge in the liquid phase with this double layer formation. And in that region, I've not only manipulated the electronic state of the metal, but I've put in place this electric field. And it's already known that that can affect the adsorption enthalpy. There are other approaches to do this, and that is to do the charge balance and manipulation of the electronic state. And so one of these is called backgating approaches, or the FET systems, which come from microelectronics industry, but we can use them in catalysis. My colleague Dan Frisbee at Minnesota works on this with me. He's already demonstrated this for the hydrogen evolution reaction under static conditions. But what you're doing essentially is creating a capacitor where you have this dielectric in between. You apply a voltage, or gate voltage, and you accumulate either electrons or holes in the metal, and that manipulates the Fermi level for when you have an adsorbate on this. And that can also be quite powerful depending on the dielectric you pick, the applied gate voltages, the metals, and the adsorbates in particular. And these things are quite fast. They can rearrange it on the kilohertz or faster timescales. So it should be possible to achieve the timescales we need for these particular systems. And I hope in a year to be able to tell you that it worked, but we haven't done it yet. Okay, so let's come back to this idea of if these are potential systems, how can we think about their behaviors? If we think about this particular system here, you can see that B star is moving a lot, and A star is moving about half as much. So this would be a high gamma particular system. In which case, when this is lower, right, that drops my transition state energy, and it's easier to get to over here. And then when I flip back, I come right off the surface. And so there are all sorts of variations of this to think about, these ratios of gammas. This is a volcano curve here at 3 different temperatures. You can see that my turnover frequency, of course, goes up with temperature. That's good. And I can see my surface coverage over here on the left. My transition here is right around 0 relative binding energy. And way over here on the left, you can now see what will happen at very weak binding materials, which is normally, I think, about having both A and B on the surface, but there's a third option where there's nothing on the surface. It's essentially a clean material. And that's important when we think about the global behavior of all possible systems. So here's a system now where I'm thinking about this ratio gamma. This is the slope of the adsorption energy between two different surface species. So gamma here could be 1, and that's where A and B move exactly together. Right? It could be less than 1, and it could be greater than 1. And in this case, I'm showing you all the plots here of surface coverage for gamma greater than 1. So here's the surface coverage. Here's my theta A. You can see theta A is fully covered in A over here. Over here, it flips over to where it's covered in B. And on this side over here, I have an open surface, depending on the ratio of how these things move together. And of course, any system I pick will have a different ratio, so I have to account for them all. And so if I think about taking all the possible volcano curves for that particular system, again, there's some things that go into this here, like what alpha I picked. I picked a pretty sharp alpha. I picked a conversion here of 1% for differential conditions. But you can see that as I move all the way from small to large gamma, as I sweep out this whole possible curve of all the scenarios that any system could exhibit for this set of alpha and beta BEP scaling relationships. And it actually looks quite complicated, but if I freeze it and show you all the possible systems together, it actually makes sense in terms of a global picture. If I think of the relative binding energy of a reaction here, I think of kind of 2 limits. Right? Over here, this is the binding energy of B star to get off the surface. No matter what I do, I can't go faster than that because there's nothing I can do except change the energy of what's on the surface. Those two should scale linearly. So that's an ultimate limit. And on the other side, this is how fast I can put things onto the surface. So every variation we see from this, my students, when I talk, it's a superposition of volcanoes, so we called it a supervolcano, okay? Every variation from the supervolcano shape has to do with a reaction limitation. So anything that keeps you from achieving the absolute possible fastest system you could go under static conditions has to do with a reaction limitation, which makes sense. If you had a system that basically a molecule stuck to the surface, instantly reacted, and then could come off as a product, you could actually operate way up here under a static system. And that's what I talked about at the beginning. If we could find that magic material that had no transition state limitation, it would be possible to do this right here, right, for some systems. But we haven't been able to find that for most chemistry, for any chemistry really. But that's the idea, is we can get around that issue where most systems here exhibit a true transition state limitation by dynamically altering the system. Now, that's an A. We just spent about 20 to 25 minutes talking about A goes to B, which is not even a real system, right? But things get even more complicated than that, and I didn't even think of this until we started exploring it. And I had to email many people, including people here at the University of Maine and many others I talked to about thinking about this. And that is that what I think I said earlier is when we take in a surface intermediate and we apply work to it to lift it up to a different binding energy state, we're imposing energy and work on the system. And that's important for thinking about the overall conversion of any particular chemistry. And that, of course, matters because a lot of the chemistries that are important we work with are equilibrium limited. Let me give you an example here. Of course, I said ammonia is important because it's favorable at low temperatures where we can't activate N2. Something like water gas shift or reverse shift here is also equilibrium limited. That's why we use those in staged different thermal systems. Something like dry reforming, that should be a 4 right there. Methane is also thermodynamically limited. All sorts of things like esterification chemistries and etherification chemistries, a lot of these things are equilibrium limited. And so we've come up with different strategies for how to deal with this: reactor separator systems, operating at low conversion and then separating products, and just dealing with these things like good engineers, which is good, of course. But what we would like to do is just make a reactor that just solved all our problems. And I'm a reactors person, so that's the approach I'll take, right? It would be good if we could take a system that would normally come to some delta G minimum of reaction, and then impose some sort of work on that particular system to drive it to a new steady state that was preferable compared to the conventional conversion of your system. So if we could do that, we would have some added work we put into our system that we could impose on it from the surface. And that would push this system to a new condition. That's not a new equilibrium because the equilibrium doesn't change, but it's a new steady state for a particular system. So this actually seems to occur in the simulations that we run. So here what we've done is we've taken an A to B reaction, we've put it into a batch reactor, And then we've imposed a bunch of different starting conditions. So this is pure B, and this is pure A, and everything in between for starting conditions. Each one of these is a separate simulation. We've imposed these conditions here. 1,000 hertz oscillation at 0.2 eV. That's actually a pretty low amplitude right there. And we let this run dynamically, and what you see is even some of these here cross equilibrium and come to a new steady state. No matter where we start from, we go to the same steady state. And then when we turn off the dynamics, we come right back here to equilibrium, just as we had better, right? I had the student add this part here just to absolutely make sure we weren't just doing something stupid, which is easy to do, right, what we do. So of course, this is unsettling because this is not the way we like to think of catalysts. We tell all undergrads that catalysts can't do this. And of course, what we should be saying to them is catalysts, conventional static catalysts where we're not adding any extra energy in, can't do this. So what's one way to think about this is you think about a system that's oscillating dynamically with time. In the strongest energy state, down there at the bottom, that's where the transition state is the lowest. And that's where the green is able to hop over the boundary to get to the yellow, right? And then when the yellow is being lifted up, right, you're preferentially pushing it over here to my B state. But it's not perfectly efficient, right? Because it's barrierless to actually come backwards here. So I can think about, I'm going to do some work here in the reaction path to put A over here to B, but that has an efficiency. And that efficiency depends on all the different conditions I pick for my oscillation amplitude and frequency. And so that's something I'm interested in right there in particular. Now, and I'll say more about this here in a minute, how efficient is a particular system. And again, I'm also open to ideas of, is this the right way to define an efficiency for a system? So let's take a single system and let's explore it. Okay, so here's my average turnover frequency. Here's the normal Sabatier curve with a maximum right there. And I'm going to impose a fixed amplitude oscillation, but I'm going to let that amplitude shift back and forth, okay? So even though it's the same width, right, it could be really high and really low over here. This is the point here where it's exactly matched in the time scales of both steps. And I'm going to use that now to screen all possible conditions. So when I do that, I get this data right here. And what you're looking at, right, this is the oscillation frequency I've put on this batch reactor. This is the relative binding energy. So this is me moving that fixed amplitude left to right, okay? And what I do is the postdoc did it, actually. He lets this batch reactor run until it stops changing. The average turnover frequency stops changing with time. So essentially, you've let this run for a very long period of time. And we look for is how this deviates from equilibrium. So green right here is equilibrium. This system's set up so that we get a 50-50 split between A and B. Okay, and that's exactly when at really low oscillation frequencies, I mean, this is really low, we actually get that right there. But what you see is depending on where we put the amplitude and what frequency we pick, we could push this reaction all the way to high conversion or keep it down low at very low conversion, depending on which way in the reaction you want to go. So you could push it one way or push it the other way. And its ability to do that depends on the frequency here, but also the position. Now there's one point here that immediately sticks out to you, right? Which is there's this point here where we transition from a forward forcing to a reverse forcing system. And that's actually that point I told you about earlier. This is the delta point of that particular system that we've selected. I'll explain why that is in the next slide. If I'm manipulating a system and I want to push it forward or backward, it's actually behaving like a ratchet. So what it's doing is it's preferentially moving molecules to one side or the other. The question is, which way is the ratchet of my particular system facing? Is it facing forward or is it facing backwards? And it actually has to do with the filling state. This is the filling state right here. And you can see that in this case, I'm preferentially filling this state over that one. And then when I flip to a weaker binding state, right, I remove molecules up into the gas phase and for A. On the other side, when I've actually crossed this delta point, now I'm filling preferentially over here. And when I flip, I move molecules in that direction. So there were all sorts of times when we didn't understand this at all, that we were starting out. We said, well, you know, the reaction runs great, but it runs in the wrong direction, right? And it didn't come together until, you know, we looked at an aggregate of data and we're like, oh yes, of course, this is obvious in hindsight, right, why it does this. But it makes it very clear and easy to figure out if you want to have a catalytic ratchet like this to move things in one direction or the other, how to think about conditions you could operate to move in either direction. And so the question then becomes, how efficient are these particular systems? And so this is the definition of efficiency we have right here. This is how our system at steady state differs from equilibrium. So it's the amount of apparent delta G that seems to exist versus the amplitude we've imposed on that particular system. And there are systems here that we have not explored this really very much at all, are giving efficiencies of 40%. What that means, I don't know yet. And I'd say this is an area I still don't really understand completely. And that's just because we've published this paper just a few months ago. And it's one of the things I want to explore further. Okay, let me end with kind of tell you where we're going in terms of the simulation space here. I've showed you kind of what we're doing experimentally to work on this. But there are much other bigger, more complicated questions here and potential applications. If I think of a system like this, right, now I have even the simplest of chemistry. I have A goes to B and I have A goes to C. And of course, I'd like to speed these things up, but probably what I'd like even more is to take a system where I haven't been able to improve the selectivity and force it down one pathway or the other, okay? So in this case, I'm gonna have two energy diagrams, and they're both gonna be oscillating, but presumably these two pathways are different, right? They're different chemistries, and they're gonna oscillate in different ways. They're gonna have different binding energies responses between C and B. In fact, this will have a gamma, and this will have a gamma. And you can think of them as having their own slopes down here on this gamma delta plot. So here's the slope for the second reaction. Here's the slope for the first reaction. Here's the delta point. That's where A and C have the same energy. Here's where A and B have the same energy. And the point where they cross here is quite important because that point right there is where B and C in our oscillation would have the same energy. And that has a lot to do with where we select for a particular system. And I can show you that right here. Here's our particular system. And what we've done is we've said, here's A to C and here's A to B on a volcano plot. And you can see that it's quite easy actually to make C, right? C is preferential way over here under static conditions. So if a system was already making C preferentially, no problem, right? Over here, I can get 50-50 mix of A and B and C. Right, and you can see this here. This is selective to C, this is selective to B at very low frequencies. So if I wanted to make B, I could do that under static conditions, but I'd also make half of component A. What I'd like to do is find a way to only make component B right here, because there's no way to do that under static conditions with this particular catalyst. And what we find is if we take this amplitude and we shift it left to right, I'm going to show this value right here. If I move that from side to side, what I find is as I cross this amplitude over the peak of either side of the volcano, I can actually resonate this reaction and speed it up to the point where I get almost perfectly selectivity to component B right there. Now, there are actually two things that are happening here. And I think I left that diagram off here, but I can show it on the next slide and come back here as needed. If I think of these three separate systems, essentially, here's my rate of conversion of A right here. So this is A that forms B and A that forms C all together. This is my oscillation frequency I've imposed from really slow all the way up to 10,000 hertz. And this is the rate at which A is converting. You can see there's two regions that A will actually accelerate. There's this big blob over here and this blob over there. And when I actually look at the independent systems, you can see that they actually resonate under different conditions. The A to B system is over here, which if I flip back here, I'm gonna go back one slide, you'll actually see that's when my amplitude sits nicely across this volcano curve. And over here, this is when I actually sit right across this volcano plot right here and accelerate that reaction. Now what happens also is that when I cross over on this system right here, I'm crossing over that, if I go back one more, I'm crossing over this point right here. And I'm not only accelerating one reaction, but I'm preferentially putting that product on the surface. So it dominates thermodynamically and kinetically on the surface. If I go forward again, you can see this again here. This point here, this region matches up with this. And this region here, even though it's weakened by the presence of a secondary reaction, in a single system, you can see it dominates right there. So where are we going with this? We're continuing to explore experiments, but we're also continuing more complex systems, because even a two elementary parallel system is still pretty simple. There are, of course, many more complexities. This is what we're running right now, and if I hadn't been so tired last night, I would have shown you some data we got yesterday that shows that you can take systems like this that are reversible all through 2 intermediates in the series. You can actually select out for different independent species. We can have parallel systems of networks. We can have, of course, bimolecular reactions and how we compete between different reactants. We could have complex mechanisms, and then we can have all sorts of bizarre dynamic behavior. Like I showed you earlier, this system that had a negative gamma, where something absorbs strongly and something else gets weaker, right? That's very strange, and that's going to give interesting behavior. And then, of course, real systems are networks, and so it's demanding to even explore 2 or 3 elementary reactions. What happens when we go to 10 or 12 elementary steps? The number of parameters here is already doubled in a conventional system, and searching out and exploring this using advanced machine learning techniques is good for funding, but also might actually work here. So, all right, that was a good joke, though, I think. All right, so this is a bigger team than just me. I work on this. My collaborator at UMass, Omar Abdelrahman, works on this. My former student, Andrew Teixeira at WPI, works on this experimentally. But there's all sorts of other things like that show up here. So exploring more complex systems requires optimization approaches that my colleague Qi Zhang and Turan Birol help with in terms of materials and both exploration of reaction networks. My colleague, or my collaborator Volcano at Delaware and his team work on this, and then Dan Frisbee and I work together on making these different backgated and electrocatalytic materials. But I started out by saying, these are the reasons you shouldn't believe this, because the promise is immensely high, which is why you should be immediately skeptical. And I think that's the right approach. But at the same time, my excitement over this is very high because I see it as a potential new way we can manipulate systems. And I will say there are things in the literature I've seen that might be doing this already. I don't have the evidence for it yet. And so there might be examples of this out there. What I do want to get to is the point where we have examples of this and we can start applying it to different chemistries and maybe using it to do things that are not possible. But of course, there's immense effort still required. How do we understand complex reaction systems, right? We've only looked at really simple systems here. We need to demonstrate tunable surfaces. We've done that experimentally, but we haven't done it in terms of the reaction networks. And we need to start exploring how we can take real systems and implement kilohertz kinetics. And until we do that, we can't merge the model with the catalytic experiments. And until we have that, we don't really have full confidence that this can work. But we're lucky in the sense that the US Department of Energy has continued to fund. This is our whole center here of people. Not everyone's working on this, only a few people are in this. But the US Department of Energy is excited by this idea. They like it, and they think that there's many possibilities for important chemistries. So let me leave it at that, and I thank you for coming today.